Wait a minute. Let me also try getting the camera on there. Nice. Let's see. Good evening. It's 7:15, so I'll start. My name is Lawrence. I'm going to talk to you about software transactional memory. So what is software transactional memory? I would describe it as garbage collection-esque concurrency control, meaning it's automatic and you don't have to think about it much, which is a real selling point, as I'll get to. That's getting a bit ahead of ourselves. So first, a little bit about me. I've dabbled with Haskell since 2014 when I was introduced to it in university, followed a couple of courses on it, and I love talking about it and introducing it to people. Currently, I'm the team lead of the DevOps team at Transactional, like the Debla said, and it's a Haskell company in Utrecht. We've been using it in production since 2017. The stuff that we use it for, it's a ton. It's really been growing for us, and it's really worked out for us a lot. We use it for job scheduling. We have some CLI tools using it. We have a reverse proxy API gateway ingress thing, which is written in Haskell. A WebSocket-enabled document store, which is actually open source, and you can check out on our GitHub. We use it for data processing. We have a merge bot written in it, and an email sending service as well. So we use it for a variety of different things. As you can see, we have on the slide, we have a tech blog that you can use to visit and see what we write about. We write a bit about Haskell, some stuff about Python, some stuff about ops itself. Some of our code is open source, and you can check it out on GitHub, and we're actually hiring Python engineers, Haskell engineers, front-end engineers, and also people doing Nix. So that's nice. But that's enough about channeling. Except that I have to say that we have some STM sprinkled around, but we didn't really we use it basically. My interest for data, I think the use of STM at Channel, it has been largely personal. I haven't done much with STM in our code bases, actually. So, about STM. I hope the sound is good. Is okay. It's saying it's noisy in the microphone. Getting a pop-up. Hope it's better. In this talk, I want to share some of the problems which are solved by STM. I want to discuss how and when STM can help you, and discuss the implementation of some STM data types. I won't get into the runtime implementation of STM as it exists in GHC because it's quite complex and we don't have time for that. But that being said, let's get into the motivation, get a lay of the land, of the concurrency land. There are two main terms which come up if you talk about making software fast, and they're concurrency and parallelism. Concurrency is a property of the program, and parallel is a property of the machine. You can have a program which can execute concurrently, but if your CPU does not support parallel execution, then your program won't execute concurrently. Cool. So concurrency is a matter of potential, and parallelism is a matter of actually things happening at the same time. And so it's a realization of that potential. And why care about this stuff? Well, speed is one reason to care about this stuff, on multi-core machines at least. And there's also UX and fault tolerance and that kind of stuff. There's this thing or law or thought process, which is called Moore's law. And it says every couple of years, the number of transistors on a chip doubles, which means that single-threaded performance doubles. You can just wait and your program will execute faster over time. But this has been hitting some walls in terms of power and the size of stuff. So this is no longer strictly true. And in order to make software fast, we need to think about concurrency. If we're going to write faster programs, then we need to care about multi-core, and STM is one of the ways that you can do this. So about the potential that I mentioned, there's some peril to it as well, because most programs use and transform data, and that's fine. That's what we write them for. And a configuration of data in a program, that's called the state of the program. And the view of the world that we have, it depends on program state. And a program, and state, those are very, they're both very important. And this state and this view of the world can be spread across multiple cores and multiple threads, depending on the configuration of your program. And that makes things tricky. These are some of the things that we want out of state. We want consistent views over the state. So we want, if we read it a couple of times, we want it to be the same thing. If we update the state, we want the update to be atomic. So it either happens all at once or not at all. And we want these updates, if there are multiple updates, we want these to happen in isolated transactions. You may notice if you're a database person or you've done a database course that this really sounds like database stuff, and it's sort of related. Just the D in ACID for durability is missing here. So the main question that we need to answer is, what do we do with state? If you're doing concurrency, and the answer to what do you do with state depends on the concurrency model that you choose, or one of the concurrency models that you choose if multiple ones are supported by your programming language. There's two main ones I want to discuss briefly. Those are shared memory and message passing. Shared memory is where you have a big chunk of memory in your computer, and you write a bunch of data into that chunk of memory, and multiple threads or executing in your program, they all read and write to that memory location. So this is, and if they want to communicate these threads or synchronize something, then they write to the same piece of memory. And you can summarize this as communicate by sharing. So these threads, they communicate by sharing this same kind of memory region in the computer. And message passing is slightly different. It's where it's mostly from actor model programming languages, Erlang, Elixir, Go, Cloud Haskell, some Scala stuff does it as well. And it's where you share by communicating. So you have these actors, and they can send messages to each other. And if you want to send a message, you include a copy, generally a copy of the data, and you give it to this other actor. It's a completely different concurrency model that I won't get into much more. But just know there are other ones than shared memory concurrency. And today we're going to cover just that, shared memory concurrency, and we're interested in sharing, and we're interested in mutation. But mutation is kind of difficult, and it's kind of annoying as well. And I'll explain why. So this has been a bit of the lay of the land. And we're now going to go into a bit of an exercise, and we're going to implement a banking system, because that's always what you do when you want to demonstrate a concurrency example. And I've called this a yak shaving exercise. So I'm going to show you some code, and it's going to contain some bugs. Like I said, we're doing banks. Apologies to anyone actually programming banks. I know nothing about it. We're just going to do it like this. We want to transfer some money. And we have accounts that we can transfer the money between. We have an account that we can transfer the money from, and we have the account that we can transfer the money to. And we're very diligent, and we're using a proper decimal type for our amount that we want to transfer. Assume that these account types have some credit and debit functions. So it looks sort of like this. Oh, and by the way, this isn't Haskell, because I thought let's use something which has syntax like this. I'll get to the Haskell. So there's something wrong with this. There's not much wrong with this if you're just using it in a single-threaded program. Should be fine. But if you introduce some threads or some concurrency, then this can go wrong. It's not a thread-safe code. So what basically can happen is while this is going on, some other thread also is executing this transfer method with the same from and to account, and they're overriding each other's values, and it's not gonna be great. So that's something that we don't want to do. So what do you do when you program with threads? Well, traditionally you use these locks. And a lock is something like, all right, please, I am the only, as a thread, you say, hey, I am the only thread that's allowed to modify this thing right now. And afterwards you can unlock it and say, all right, I'm done with this mutation or this critical amount of work. It's free to be modified by other threads again. And in between, you can assume nothing modifies these to and from things. So does this solve our problem? We first lock the from account, then we lock the to account, and then we unlock, then we do our business logic, and then we unlock again. Some experienced multi-threaded programmers may note, no, this is not correct either. And that might be surprising. Is there something with this lock thing that is the implementation incorrect? No, the implementation is absolutely fine. The problem is that this is a deadlock trap. So this is what can happen. If there are two threads, thread 1 and 2, that both try to execute this transfer method or function, and they do it for the same accounts, just flipped, then what can happen, is that right in between the call to the first call to lock and the second call to lock, the other transfer method was executing as well. And it tried to lock the two accounts. And if that happens at just the right time, then your program will be, it will have a deadlock. It will be unable to make any progress. And generally, if you're in the business of production software and providing service to clients, this is pretty bad. So in programs like this, you generally need to decide on a global locking order. So let's say you use the IDs of the account, and you always lock the account with the lowest ID first. Then you can write this method, and yeah, it'll work out. But notice, first of all, that we spend an awful lot of code on this concurrency thing and making sure that goes all right, as opposed to the business logic we have. And there are some other sources of difficulty in writing this stuff as well, like actually remembering to lock everywhere where it's required. If you forget, you get garbage. And what if there's an error which happens while executing this code? For example, you try to debit an account more money than that's in the account. What happens then? And how do you unlock everything again? That's tricky. So assuming you get all of that right, assume you have this perfect transfer method function thing. Then I ask you, how do you use it? And that's maybe a bit stupid, or it appears to be a bit stupid, but I have a point. How do you use it in a transaction with complex logic without causing problems yourself and without knowing about its internals? I suggest that you cannot. You need to know about the internals and about the locking order and how those logs of the function pertain to the locking state of your global program in order to reason about it in any meaningful way. Otherwise, you're just going to cause more trouble. So your control flow sort of gets turned inside out. You cannot have abstraction if you have concurrency in a language like this. So I say concurrent code is where composition goes to die, your encapsulation goes to die, and maybe also, depending on whether this is your favorite pastime, your sanity goes to die. So that's a bit sad. And I hope this serves to illustrate the problem that I think is worth solving. Or, well, I didn't solve this at all. Like, this is all work of other people. But this is the problem they thought was worth solving. So, is there light at the end of the tunnel? Many things come with, there must be a better way, right? Remember I mentioned garbage collection. Well, most programmers don't use malloc and free, or most programmers in high-level languages don't use it. Or you use Rust, and this isn't a problem at all, but I'll pass on that. In most high-level languages, there's a thing which is called a garbage collector. And the garbage collector takes a look at your program and decides when to allocate in free memory. It decides when to free memory, sorry. And this sort of made this whole traditional source of bugs, malloc allocating and freeing memory, it made it go away. So why can't we do something like that for concurrency? Like, make the computer handle it. Don't bother me with all this locking nonsense, please. So that's the question that STM aims to answer. What would it look like? Well, if our fake language has this magic keyword atomically, where atomically does all the right things, I would want it to look like this. We have a transfer function. It takes both of these accounts and the amount again, and we atomically credit and debit the amounts, where atomically takes care that if there are exceptions or anything else weird happens, that this just, it works. Yeah, that would be very nice. But this is a fake language. And this is way too easy. I'm probably making stuff up. There can't possibly be a language that works like this. Well, actually, oh yeah, atomically it has all the properties we want. But actually, let's switch to some code that you can actually run. It looks like this. And this, well, this is suspiciously looks like Haskell. And given that this is the Haskell Amsterdam meetup, it probably won't surprise you that it is. We have a transfer function right here. We get these accounts. I'll define the type in a bit later. And it takes this amount and it returns this STM unit thing, which means an action or an STM action which has no result. And in order to, and the definition of this function simply reads, credit the receiver the amount and debit the payer the amount. Very nice. But you can't run this like this. You need some imports and a main function in Haskell to actually execute code. So let's have a look. First of all, notice the import control concurrent.stm. It contains the STM type and also this function atomically. It's below. And atomically has this type where it takes an STM-A and it produces an IO-A. So it runs this action in the STM mode. So if you transfer foo from foo to bar 300, 300 units, money, whatever, then that has the type STM unit. If you put atomically in front of it, it becomes IO unit. And incidentally, that's the exact return type that a Haskell program needs. But I left some stuff out, so what's in here? First of all, the account type. It's a TVAR, which means transactional variable. You can put all sorts of things in a TVAR. In this case, I put in a decimal from data.decimal. And if you want to create these accounts, it reads like this. You create a new TVAR while you're in IO, and you give it some amount, or this initial value. So here we have foo, which is a TVAR decimal, or an account, containing 4242 money. And there's bar, which contains 5,000 money. And here we transfer this, this bit of money, right? So that's sort of how it reads. And I tell you, this is actual mutation in Haskell. You may be used to Haskell being a pure functional programming language, and some people confuse that with it doesn't allow mutation. It clearly does. Or at least I didn't print anything here, but trust me, it does. So let's discuss some of these semantics of this magic function, which takes an STMA and gives an IO. It mutates any STM variables, and it guarantees that external observers never view intermediate states. So I never see that. This is the consistency part. If I am in the middle of transferring money from one account to the other, and I've debited the first account but haven't credited the second amount, that kind of intermediate state is only visible, it is not visible to any external threads or observers. And transactions complete successfully if there aren't any conflicting changes. I'll define conflicting changes in a bit. And if there are any conflicts or conflicting changes, like any of these TVARs has been modified by one thread while the other one was also doing something with it, then the whole transaction, the entire STM thing is retried. So that sounds pretty good. So how do we actually know about conflicts? This slightly gets into runtime details, and I don't want to spend too much time on this. But basically, the runtime maintains an access log, and it records reads and writes to these transactional variables. During this atomically block, it just executes at will, and at the end, it checks whether the transactional variables involved were modified by any other threads. And if that's not the case, it can commit. And this access log thing, that's actually also how relational databases implement transactions. It's kind of a lot of parallels. And two transactions conflict when their write sets overlap, so they write to the same transactional variables, or when one of the transactions' write sets overlaps with something that the other transaction is reading from. That also is a conflict, and it means that you can proceed with all the writing business, but you need to retry the read, and the runtime takes care of that. So how does retrying something work? Well, you jump to the start of everything, so the beginning of the STM block, and then you try again with the new values of these TVARs. And the runtime, if you call atomically, it will just retry and retry and retry and retry until it succeeds. And this helps you when there's not a lot of conflicts, or this helps you resolve conflicts. And it's actually a very nice design if your program doesn't write to the same memory regions from multiple threads all the time. That's what I mean with there isn't a lot of contention. Otherwise, there's some issues. I'll mention that later. And retrying is actually also the error handling mechanism within STM itself. If you enter some invalid state, or you cannot debit or credit an account because you cannot debit an account because there's not enough money, then you simply retry the transaction and wait until the account does have enough money. Because this would be an implementation of debit. We take an account, the amounts we want to debit, and we use this read TVAR function. It's a monadic, it returns an STM decimal in this case. We bind that into balance, and then we write to the same transactional variable the balance minus the amount we want to debit. So you don't always, so the problem here is that you can overdraft an account. Basically, the account balance can drop below 0. So we want to handle that edge case. I just mentioned we have retry, which is this function from STM. So right here we can compare the balance or the future balance minus amount. We can see if that's lower than 0. If it's lower than 0, then we can retry the entire transaction. And if it's not lower than 0, it means we're all good to go with our debiting. And we can write to the TVAR the new balance. So the semantics of this retry function are just retry the entire transaction from the start. Go to the beginning of the parent-most STM thing, function, and just try there. There's an asterisk here. I won't discuss it, never mind. And it ensures that we don't have to undo all of our previous work to remain consistent. Because remember, in our locking example, if you have an exception or an error case in between a very complex nested transaction, and you want to get out of that, you not only need to unlock, but you also need to reset all the values of the stuff that you modified to their initial values. Otherwise, external observers can see the results or can see intermediate states. So retry has some very, very, very nice properties. And additionally, the Haskell runtime will only actually go and retry the STM transaction from the beginning if any of the inputs change. So otherwise you risk having a buzzy wait. Like, for example, try and debit someone 1,000 money when they only have 10 money. Then if that remains the case, and you go have a naive implementation and just go to the beginning and retry, and go to the beginning and retry, and go to the beginning and retry, then you're very effective at turning electricity into heat, but your programming is not really doing anything useful in terms of your business logic. So this, the Haskell runtime takes care to see, hey, when did these, it will only retry your STM transaction when any of the involved variables change. And that's also a nice problem. But sometimes we don't want to retry perpetually, right? It would be also very nice to be able to say, hey, this person doesn't have enough money, period. Don't retry, just give them an error message. And that's also something you can do in STM. And there's this function, which is called or else. And it basically takes two STM actions. And if the first action succeeds, then if the first action succeeds, then the first action is the result of the entire thing. And if the first action retries, then the second action is the result of the entire thing. But if the entire thing, including the second action, also has to retry because some of the involved inputs have changed, then the entire transaction is retried as a whole. I hope that's clear. Otherwise, the docs have a nice explanation in text, which is probably easier to understand. So this allows you to, and you can also return a value out of a transaction to indicate success or failure. Here's an example, might be easier. We have this transfer function again. If we don't want to retry perpetually, for example, because the debiting doesn't work, then we have this or else thing and then a no-op. So we first do our actual transfer. If this fails, then we do this no-op, and no-op is just return, is just jury unit. And you can also write it like this. There's an alternative instance for STM. Cool. So brief recap. Let's see how I'm doing in terms of time. Nice. Still have time for the rest. Brief recap. STM gets us atomic transactions for shared memory. It gets us sane control flow, so you don't have this flipping your control flow inside out, or the depth of encapsulation or composition, that kind of thing. And it helps you avoid common locking problems. And it works by keeping a transaction log, checking all the variables involved, and then retrying end conflicts. The combinators are atomically, retry, and or else. And I actually only showed you transactional variables, but in the rest of the talk, I'll show you a few more. But before I get into the rest of the data types, I think it's good to maybe answer any intermediate questions that might be there. You can post them in the chat, or you can post them on YouTube.
I'm keeping watch on the YouTube chat. If I see any question coming along, I'll let you know. But so far
it's all right.
But so far, there is no question from YouTube.
Okay. In that case, I'm just going to assume everything is clear, and I'll continue with the rest of the data types. So I've discussed transactional variables, right? But you might want to do more than just store individual values. So it's what the slide says. TVARs are nice, but sometimes we want something more, because more data types give you more possibilities. That's always nice. And there is this STM package, which is written in Haskell itself. It provides a bunch of data types. And they're all built on top of these TVARs. So that's what the rest of this, my slide deck is about, how you can make fancier data types out of TVARs. So some stuff in STM. The transactional variables that I mentioned. These actually require runtime support to work correctly. There's tarray for arrays. There's tmvar, which is a variable which is either empty or full. It's named this way because Haskell also has an mvar without the t. I'll get into what the difference is in a bit. There's queues, bounded queues, and channels, which are kind of like queues, but they support broadcast. I'll hope to cover at least the tmvar, and if there's time, we'll get into tqueues, and I also have a note about maps. Cool. So tmvar, what is it? A tmvar A, is either empty or it's filled. And you can put an A in it. Just like we had tvar A, we could substitute the decimal for the accounts, which you can put in strings or whatever. And One of the things that this does is you can put something in the TM var, and if it's empty, so that's this put TM var function. This will block, or it will retry, STM retry, until it's able to put something in the TM var. And you can only put something in the TM var if it's empty. After you've put something in the TM var, you cannot put something else in it before you until you take it out with take TM var. It's this other function. And take TM var, it also blocks if the TM var is empty. And you can use these kind of things to synchronize stuff over multiple threads within STM transactions, which can be really cool. And the question I want to answer is, can we build this TM var thing ourselves? And the answer is yes. And you can even write it yourself in Haskell using just tvars. Because this TM var is basically a tvar containing a maybe a. So if you add a new type over this, that's the actual implementation from the STM package. So this is, I removed the comments, but something like this is in the STM package. So a TM var is a new type over this tvar maybe a. And if you want to create a new TM var, you first got to give it some contents. Yeah, it's what it does. It creates a new transactional variable with just contents, and it returns the tvar wrapped in this TM var new type. That's actually the implementation, which is really cool. And if you want to create an empty TM var, then you use nothing instead of just. So these are pretty related. Yeah, and if you want to add something to the TM var, in our TM var module, we unwrap the new type. We have the new contents to put in. We read the inner transactional variable. If it's a nothing, then we're good. It's empty, and we can put something in this TM var. Namely, we can use the write tvar function to write to this inner transactional variable the just with the new contents, and then we pure unit to signal success. And if the contents of this TM var were actually non-empty, so if there's a just in there, then we retry. And STM will take care of the blocking and the locking and all that sort of thing. Taking a TM var is similar. We swap the reads for the writes. But this case, if there's nothing in there, we retry. And if there's something in there, then we empty the inner transactional variable and we return the contents. So that's how this works. You can initialize them empty, you can initialize them with some contents, and you can write and put contents. But I mentioned that these things come from mvars. They owe their name to it. So I think this is actually a good point to get into. mvars are not really related to STM, but sometimes they're a better fit. mvars are defined in control concurrent mvar, and tmvars are defined in control concurrent.stm.tmvar. That doesn't help by default, but it at least gives you a link to the docs. Anyway, mvars predate tmvars. So is there anything good to mvars themselves if they're just older by 10 years? Well, one thing that mvars do that tmvars don't, is that mvars guarantee fairness. If you have multiple threads in your Haskell program and they try to write to using STM to the same tmvar, and there's a ton of threads, basically, all doing this to the same poor TM-var, then there's no guarantee by the runtime that all of those threads will eventually finish, or that anything will finish in a reasonable time. And these Mvars, they do have this kind of fairness guarantee. Let's see. I'll get to the questions in a bit. I'll first finish this point about TM-vars and Mvars. So the fairness here can be important depending on your application. If you have a lot of concurrent threads and they all write to the same memory region and you need to do a lot of synchronization and you need fairness, then Mvars can be a very good choice. If you don't need any fairness because of the architecture of the concurrency in your application, and you want these nice STM features and retries, that kind of thing, then you can use the Mvars. So Mvars are a lower level tool and they can be used against starvation. TM-vars are a high level convenient interface. Cool. That's the point I wanted to make about Mvars and TM-vars. I am not sure if I can move the video to the top right. I will be sorry about the video covering the content, but I'll share the slides afterwards. So if it happens again, you can have a look at the slides. And is it possible to have a nested transaction context? In other words, is it possible to compose these atomically combinators? You cannot compose these atomically combinators because once you go from STM-A to IO-A, you're in IO. But what you can do is have different functions that all have this STM return, STM type. So you can use multiple STM functions, basically, or values or scripts or monads. You can compose them, basically, but only in the STM context, not in the IO context. On performance, how does it compare with other approaches, say actors? For performance metrics, I'm going to say, so sometimes for performance, you need these Mvars if you have a lot of contention. In terms of what the runtime implementation does in Haskell versus some other implementation in some other language, I'm not sure. You have to look at benchmarks. I believe there's some benchmarks in the paper. It's called composable memory transactions, but it's also at the end of the slides. How am I doing for time? 2 more minutes. Okay. I'm not going to get into the queues then, which is a shame. So I'll skip.
I think you could actually take your time because I think I'm enjoying the talk and I think people are also enjoying the talk. So don't feel too pressured to rush it.
All right. Thanks. In that case, I'll go for this content also. I'll take the time. And if anybody on the stream or in the chat is getting tired and they have other stuff, then go do your other stuff, of course. Nice. So TQ. A TQ of A is an unbounded first in, first out queue. And it's basically a queue wherever you have, if you want to put something in the queue, and then you can take it out. And it's in order. So the first thing you put in is the first thing you take out. And it's unbounded, so there's no max length on anything. I have some notes on that later. And this thing supports constant time inserts and reads. And the reads are amortized, or maybe also the inserts are amortized. Not sure. We can have a look at the implementation. We'll see. This interface is, again, pretty similar to what we've seen so far. You can create new TQs. You can write to a TQ, you can read from the TQ, and the read from the TQ, it blocks if the queue is empty, basically. So, question, can we build a TQA ourselves? Yes. We can use two transactional variables of lists. So it would look something like this. This time we're using data instead of new type, but because this isn't a new type wrapper, it's like an actual data thing. And there is, like I said, two tvar lists. And the first one is waiting to be read, and the second one waiting to be read, sorry, and the second one is to be written. And we need two tvars because it helps with the amortized constant time reading and writing. So we have this here. Again, I rephrased the data type. Let's initialize one of these TQs. This is pretty empty, pretty much boilerplate. We initialize read and write as empty tvars with an empty list, and we return this wrapper over this TQ. But we return this TQ data type and we pass read and write to it. So if you want to write to a TQ, well, if we want to write to something, we don't need to read end, so we pattern match over this TQ thing. This was the first list, remember, was for the elements that are waiting to be read. The second list was for the elements that we have written. We only need the second one. And then we have this element that we want to write to this queue. Well, list end. Yeah, I could have chosen a better name here. But basically, we read the transactional variable of this list of written elements, and we prepend our newly the element that is written to this queue, and then we write this back to the tvar. If we want to read from this queue, then it works a bit different. Obviously, we need the read end and the write end this time. We first we take a look at, are there any elements that are waiting to be read? If that's a list with any elements in there, then we can take the top, the head of the list, return it, and write to this tvar the tail of the list. So we take one element out of the queue that was waiting to be read. However, the tricky case comes here. If there are no elements that we want to read or that are ready to be read, what do we do? Well, the high-level spec is get the contents of write, reverse it, store that in read, and retry if write is empty, because that's retry if write is empty because we promised this blocking operation. This is where the amortized comes from. So it's not O1 for any operation. It's averaged over over a series of read and write operations. The read and write operations cost, they have constant time. They take constant time. And there's some Haskell that you can write here. I didn't put it on the slide, but that's the gist of it. Cool. So we have these queues. They can go and grow very large. There's no bound on these things. And a bound means, it's a number, and it says this is the maximum amount of elements that this queue can contain. And that's, in practice, it's very handy to have bounds on queues, because if you don't have bounds on the size of your data types, then it might be happening that there's a writer part of your program which is adding elements to this queue, which is producing these elements much and much and much quicker than your program can, than the read end of the queue can process. And if this happens, then your memory usage of this queue will, it will grow and it will blow up and maybe even crash your program or cause it to be OOM killed. And if you add a bounds on this queue, then the writes to this queue, if it's full, it will block. And again, this is this STM retry operation. And this is very useful if you want to have back pressure in your systems, because it ensures that you have constant memory usage, and that if there is a part of your program which produces values to be put on this queue much more quicker than the reader can consume them, this retry and this block causes back pressure, and it all balances out. So how do you add bounds? Well, you need to know the sizes of the read and write lists, and you can keep track of these in this DB queue thing. So you have a read capacity and a write capacity, and you can add some if statements which basically check whether these capacities are all right before continuing. And there's some values that we can initialize again. This is basically rehearsal of what we just did, but basically, if you write to a queue, there's this if statement. You first check if the queue isn't out of capacity, you can, if that's correct, then you, if the queue still has capacity, then you write that the queue has one less capacity, and then you put the element in the queue again. There's some question about what should go here, I believe. Yeah, exactly. We figure out if there's any read capacity left. We retry if there's not any read capacity left. But if we have some read capacity, we can swap read and write capacities and subtract one. Doing this in a talk format and explaining the invariance here, it's not really worth our time. You can either go look at the implementation or and verify for yourself that this makes sense, I guess. So I'm going to move on here. This is the implementation. It's also in the package, STM package. You can look at this for us. Cool. So STM containers, finally, brief couple of notes before we wrap up. I promised I was going to talk about maps. And let's think about it for a bit. We've seen transactional values of lists. We've seen transactional variables of regular, like decimals or maybes and that kind of thing. But sometimes you want a map. And this can be useful whenever any hash map is useful. For example, you can use a user ID for rate limiting information in your reverse proxy that you're writing. Just an example. If you want to implement this, the first idea might be to put a regular hash map in a tvar and put more tvars in there as elements. This allows you to modify each value of the map separately, or you can get to these nested tvars, but this entire construction is not very ideal. Why isn't this very ideal? It's a bit involved to explain, but the basic idea is if this hash map gets a lot of traffic, and traffic means if there's a lot of threads all doing things with this hash map, they all invalidate this top level tvar, or they all those STM transactions conflict with one another, especially if you have writes. So updates to individual keys are fine, but updates, that's great. but updates the entire hash map. They change the outer tvar, and for some workloads, if you have key addition or key removal, then this can give you a lot of contention. And the contention is where your entire program cannot make any progress because it's mostly spending time bookkeeping and retrying STM transactions, which keep repeatedly failing because some other STM transaction is also going on the same data. So if you want to decrease contention in hash maps like this, it requires splitting the workload into some chunks. We're not going to get into the into the actual implementation because it basically means re-implement that to be STM aware. But the data structure that you can use is this thing which is called a hash array mapped tree. And yeah, that sounds scary if you don't know what it is, but the gist of it is this. Each key value pair is stored by hashing the key, which gives you a binary value. Like you can hash something and it yields a fixed length binary value. And that hashed value you can store in a tree. And there's this blog post which introduces this, but this picture might also help. So this is a tree which stores a couple of values. Up top, like this is a value, this is a value, and this is a value. If you want to add in this hash array map tree, every one of these layer pointer changes would be a new tvar. So if you want to add a new key to the, which incidentally has a hash which starts with 0, 1, then you can add it and just modify the stop layer. You don't need to modify all of this. So if there's two threads which are doing STM transactions concurrently on like this layer and one on, I don't know, if there's another node right here to the side, and there's another one going on right there, then those transactions, they don't contend with one another. And that's a really nice property, which makes things fast. So if you are able to isolate updates to a part of the map, then you sometimes just need to insert new levels, but this is way better than having this global contention on this outer single tvar. And the real implementation is, of course, more involved because there are some clever tricks that you can do. And if you want to know more about this, which I really recommend this post, then you can check out Nikita Volkov's work, and it's called STM Containers, which has an implementation of this data structure. So that was a whole lot of stuff. Let's summarize again. I first want to say, just like garbage collectors, STM is no silver bullet, but it has some very nice properties. You still need to sometimes reason about how the runtime works and how, what this contention thing is and how you need to architecture programs in order to not run into that trap. But I would say that it makes writing some concurrent programs a heck of a lot easier than doing all this fiddling with blocks and that kind of stuff. So STM can take away some of the pain, but just like a garbage collector does not, it can take away some of the pain of doing malloc and free. You also sometimes need to know about the garbage collector's internals if you want to make it really fast. So examples of this are the starvation and the contention of long-running transactions that I mentioned. And having to keep your queues bounded, that's not really a problem with STM itself. It's just like a design thing that you probably would be nice to keep in mind if you ever need to do this. So we've discussed how you can make other stuff out of tvars. We've discussed TMVars, which are just tvars with maybes in it. And we've discussed GQs, which are just two TVAR lists. You can add bounds to it if you want. We saw how that works. And we also mentioned STM containers, which works with this hashery in that tree, and that avoids contention. That is a lot about what I wanted to say and what I wanted to talk to you about. So I would like to thank you very much for listening. If there's any questions, you can ask them on YouTube or on the meetup in chat or whatever, and I'll try my best to answer them. And oh yeah, sorry, the stuff that you should also check out. We didn't discuss the implementation in the runtime, and we also didn't really specify mathematically what the operational semantics of STM are. If you want to know about that, then you can read this paper. It's called Composable Memory Transactions by Tim Harris and Simon Marlowe or Beaton Jones. Look it up. And it was the basis for all of this work. This is my contact info if you need me after this talk. And I guess we can open up everything for questions if there are any. Thank you.
Thank you very much. So yes, questions if you have any. If you're in the call, you can ask by using your mic, or you can type it in the chat, whichever one you prefer. And I'm on the lookout for YouTube. So if I see any question, I will let you know.
All right, cool.
Let's see if there's any question.
I have a quick question, if it's okay.
Yeah, of course.
So thanks for a great talk. I was just wondering, do I understand correctly that because we are in Haskell and we have this STM monad, so we are very, very safe when it comes to what can get retried, right? So we cannot have any arbitrary I/O actions inside our STM actions, right? So when the retries happen, we kind of can be sure that we don't do anything that we shouldn't be doing, that cannot be done multiple times.
Yes, that's correct. So you can go from STM to IO, but you cannot go from IO to STM. Yeah, unless you use unsafe perform IO, because then you can take an IO A and turn it into an A. Yeah, I believe the docs mentioned there are ways to use unsafe perform IO and atomically correctly together, but you must take really great care to avoid nested calls to atomically, because that really breaks. So I guess, yes, because we're in Haskell, it gives you this certain amount of safety. It's not, the type system still provides escape hatches because it treats you like an adult or like an engineer. And if you really need to, you can do unsafe perform IO in friends. But if you don't want that, or think that's bad practice, then you can put a CI check on your code base and use like grep to filter it and find out whether anybody on your team is naughty.